Hello and welcome back to our Common Lisp project here. Last week we had a look at building the beginnings of our interpreter, and this week we're going to add in the interpreter loop. And because this is a project and challenge rather than a tutorial, I'm going to leave some things for you to attempt in the coming week, and I will look at how to solve those in the next video. So I'm going to run through the core bits and pieces to write simple programs, and there's going to be a couple of functions I'm going to challenge you to write yourself, and then you can see if you wrote something similar in our next video. But something I want to say before we get into this video, I am running a competition. I've posted this on Twitter. I've not put it on YouTube because I didn't have the competition ready at the time the last video was produced. So I'm running just a bit of a hackathon here. I'm giving away a copy of Konrad Barsky's Land of Lisp, just as a thank you to everyone that supported the channel so far. But I don't like these competitions that are like, share, and subscribe, and then you can be in with a chance. If you are not a subscriber, you can enter this competition. I don't care. If you're watching my videos, if you're sharing them, great, I appreciate it. So if you want to take part in this competition, I've got a link in the video description to a Git repository. All you will do is you will build a game in Common Lisp. It can be a simple number guessing game, it can be a dice game, it can be an OpenGL game for all that it matters. You can go as simple or as complicated as you like. It's just to apply some of the lessons that we've got here, get you writing programs in Common Lisp, and I'll pick a winner at random. First person will get a copy of the book. 2 runners up, I'll give you notepads and some pens, because those are very valuable tools when you're writing code. So if you check the video description, I'll have a link to that with the rules. Please do enter it. I'd love to see what you come up with. So yeah, thanks for supporting the channel. Hopefully someone will win a book. But for now, let's actually get into this project. So where we left off last time is we built these 4 functions here. We've got our add, our subtract here, our multiplication, and our division function here. Now, because each of these returns from the run function with the change state of the program, this is not an interpreter loop. So what we need to start doing is building an interpreter loop so our program will run and only terminate once the program has said it's ready to terminate. And we're not going to do this recursively, we're just going to use a simple do loop. So we're going to say do program counter is equal to 0, and then all we're going to do is we're going to say if 0. Now how did I do this? I've got this written down because I'm very forgetful. Yeah, something like nth program counter program, and then we want to return the program. There we go. So where we have the program counter in the let, and we never really we added to it, but we weren't using the program counter. We're going to declare it here in the do, so that initially gets set. And if you remember back to when we were writing loops in Common Lisp in the loops video, we had a step, so every time the do loop reran, we could do something with this variable, but we're not. It's optional. We don't want to update it because every function will update the program counter to something different. So there is no point having the do loop control that. And this is our exit condition. If the program counter happens to rest on something that is a 0, we're going to terminate the loop, and we're going to return the change state of the program as the output. So all we really want to do here is copy this, paste it in there, and I'm going to get rid of the remains of that let there, tighten that up, and there we go. So this is what it should look like. So I'm going to evaluate this now, but I have a sneaky suspicion that it's not fully working yet. There we go, I've got an unbalanced paren. There we go, I've got that balanced now. So we have this compiled, and what we need to do is we need to get rid of these return lines because they will terminate the interpreter loop irrespective of whether we're ready or not. Oh, irrespective of whether we finished the program or not. And because we were checking for a 0 there, we don't need to do that anymore because the do loop is managing that for us. So we're going to run that, compile that up. So this should all be in place now. If I run this, I'm kind of sort of expecting things to break. Program. I don't have any references to code. Okay. Let's get the REPL up. Let's try a simple example. I'm going to add the value stored in 1, which is 1, with the value stored in 1, which is 1, and we're going to store it in 3. 0, 1, 2, 3, which is ourselves, and then we're going to end on that 0 there. So this is what the output program should look like. This 3 should flip to 2. Unidentified operator 101. So why is that the case? So the program counter is 0. We start this loop, we end up here, is the nth program counter of the program equal to 101. It should be. So why is this not working? So if we get the first element from the program, so let's just format T and let's just get the nth PC program, and we will abort that. We'll compile this up and we'll run this again, and it'll still error of course, but we'll be able to inspect and see what we got there. So we got 101 and then we got 2. So did we get here? Let's try that. Format T. So again, we'll quit that. So we got here. So should be 4, I believe. And I'll tell you for why. Because we need to account for the extra arguments. We've got 3 parameters, that, and that, and we need to account for that as well. So we would add 4. So 1, 2, 3, and 4 should end on the 0 there. So we've compiled that. Yeah, there we go. So if I get rid of that and that now, if we run this and I interpret that, we get 101, 1120, which is what we expect. 102, 1100, which is what we got. 103, 2240, which is what we expect. 104, 56, 1022. So all of this is now working as expected. So let's try something different. Now that we've got these programs that run once, we can now try and expand this to programs that will run more than one thing. So I'm going to say another add instruction here, and I'm going to say the value stored in 3, with the value stored in 3, and I'm going to store it in 1, and then I'm going to terminate the list. So going to paste that down there. If we run this, I would expect, if we look, that would be 1, 1, 2, 101, 3, 3, and we're going to store it in 1. So that would be 1, 0. So now 1 should become 4. And then we have 101, 412, 101, 3310. So that's actually working. So where we would normally have just terminated here after the instruction ran, we've actually now read one instruction with its arguments, and then we've moved the program counter to the next address in memory, and we've read that this is an add instruction, and we're going to add the value stored in 3, which is that, and that is 2, because as the programs ran, this has become 2. With that, which is going to be 2, let's store it in 1, which is there, and then we terminate the program. So we can now have arbitrarily lengthed in functions here. So we can build long, complex mathematical operations. Nothing too crazy here, and I do apologize. My phone is just, I don't know what's going on. It's just work is buzzing me with all sorts of stuff there, but it's got my timer on it, so I do apologize for the buzzing you can hear. Anyway, we have these 4 mathematical functions. Now the challenge that I want to assign for you all is I want you to write 2 more instructions here that are going to be 105 and 106 respectively, and I will tell you how these are expected to run. 105 is going to be an increment operator, and 106 is going to be its complement, a decrement operator. And I want increment to take an address, and all it will do is add 1 to the value stored in that address. So an increment program will look like this. So 105, 1, 0. So 105 will increment the value stored in 1, which is 1. So this is going to actually become 105, 2, 0. And again, its complement 106. Here. Now you might take special note here that this does not have a 0 in the return position, because 106 will decrement the value stored in 2, which is 1, so that 1 will become a 0, and when this jumps over, having moved 2 places, the program counter 2 places, so 1 for the function, 2 for its parameter, and end up on that instruction, which will be modified to become a 0. And I'll start you off a little bit here. You do EQ nth PC program. You'd have 105. Then you would do something here, and then you would, get your arguments. You'd set the program counter by 2, and then you would do the same for the decrement. So this is going to be the increment, and again it will increment an address by 1, or the value stored in an address by 1, or decrement a value stored in an address by 1. So it's like a +1 or a -1 operator. So that's what the challenge is for you to have a look at. And the reason that I'm adding this is when we start adding more complex programs, this convenience increment and decrement is actually going to make writing the programs a hell of a lot easier. So we're just going to put these convenience functions in place, and hopefully, because it's not so much of a big deal, it's something you'll be able to figure out just by playing about with this. It's not all me building this project up. You have a chance to explore and put your own ideas into this. So I hope that that's been interesting. I really do apologize for all the buzzing. Like, I do not know what's going on. It's lunchtime. I am so sorry. But yeah, that's our video. Please do join me in the competition. I'll get the link in the video description below. Have fun with this project, and I will see you in the next video.